Good afternoon. My name is David Browning, and I work for Enveritas, a non-profit organization that provides sustainability assurance for coffee supply chains. Let me start by thanking ASIC for hosting this conference. We greatly appreciate it. We were asked to conduct some empirical research into the following question: how many coffee farms are there in the world? If I Google how many are there, a typical answer I will get is 25 million. But is that correct? Is that number credible? It seems to be. Many reputable sources have reported this number: the New York Times, ICO, PBS, and more. But whose estimate is this? What happens if I click the footnote to check the source, and then click that source's footnote to trace this number back to the original source? What do I find? In most cases, there is no footnote provided, but sometimes there is, and if we track those back, we arrive at a small handful of research papers written around 2001 to 2003 during a crisis of low coffee prices. But none of the papers I could find offer a source. There seems to be some ambiguity as to whether the 25 million number was referring to farm owners or farm workers, but we'll come back to that later. Earlier than this, there is a single paper in 1999 suggesting 20 million that provides no source, but whose author may have Googled this one earlier blog post from 1995, which offers 20 million as a number, but also with no source. And then the trail runs cold. And so, to the best of our knowledge, there is no published source of the data or methodology for this frequently quoted number. There is no footnote. From conversations we've had, sometime in the 1990s, a group of coffee origins submitted national estimates to the Association of Coffee Producing Country, and at least some authors had access to these. Country-specific numbers were never published to our knowledge, and all records were lost after the association dissolved in 2002. We don't know if all the countries submitted an estimate, but even if we had access to that data, there is no guarantee that the numbers were compiled in a consistent manner across the different countries. Did the number for each country represent farms, farm owners, farm workers? We don't know. In our efforts to track this source down over several years, many coffee industry practitioners suggested that it would be beneficial to construct a robust estimate that researchers, industry practitioners, and civil society could use, and document both the national estimates and the methodology employed. So we undertook to do this with the very generous support of the Benckiser Foundation. We interviewed more than 20,000 farm households and conducted analysis across 20 countries. We consulted the expertise of over 80 institutions and then applied statistical models to develop productivity and farm size estimates to develop a global estimate. The project took us over a year to complete and included the efforts of many of the Enveritas team across a range of countries. I'd like to take a moment to thank the many institutions that contributed to this work. And this does not represent a complete list. My apologies to those who contributed to the work but whose logo does not appear here. But I did want to provide a sense of the broad collaborative effort that this project required. We could not have completed this project without their help, expertise, and patient counsel. So thank you. First, a caveat. The result we have arrived at is not a perfect number. With greater effort and expense, we could have developed a more precise answer. But we did what we could with the time and resources available to us, and we believe the result is a credible estimate that is an improvement on the number in common use today. Over time, others may improve this number in the time-honored tradition of the scientific method. This approach to science has always played a vital role in furthering understanding of our world, and if you are sometimes disheartened because it seems that this approach is under assault from voices that argue from a position of dogma or unsubstantiated assertion, or use their power as a weapon to bully and intimidate, we can perhaps console ourselves that this is not new. Galileo had his critics too. And second, a few definitions to avoid ambiguity. We have provided an estimate of farms, not farmers. Why is that? If we take the case of a widowed farmer, it's easy. One farm, one farmer. It's also easy in the case of a husband and wife who both contribute to the coffee farm. Two farmers, one farm. But what about a wife who farms coffee with a husband who lives on the farm but is not involved in the coffee, but rather owns and runs a bakery in town? Is he a coffee farmer? And what about the farmer's father, now elderly, who lives on the farm but is unable to do physical work on the farm anymore, but does contribute by keeping watch over drying coffee during the harvest? Is he a farmer? While the woman's son works as a taxi driver in town, but comes back for 3 months every year to live on the farm and harvest the coffee for the family. And his cousin, who works year-round on the farm, doesn't get paid, but rather gets a share of the coffee proceeds, while the daughter lives on the farm, studies at university 3 days a week, but comes back and helps out on the farm the other 4 days of the week. You see the complexity. And so to reduce ambiguity for this exercise, we measure farms, not farmers, to more closely approximate a mutually exclusive, collectively exhaustive answer. Other researchers may choose to build on this foundation to explore the question of farmers and their composition, but we wanted first to provide a foundation from which others could build. In addition, we excluded coffee farms that produce only for their own consumption, where their inclusion would distort the data. We did this because the global farm number is most frequently cited in terms of interactions with global trade. For example, how many people rely upon coffee. These conversations are generally economic in nature and not referring to farms with 5 to 10 trees in the backyard where the owner picks the coffee and roasts it for their own home consumption. Our analysis did not cover every single coffee origin in the world, but we did cover most of the world. We analysed coffee origins that account for 80% of the world's coffee farms and over 90% of the world's coffee production. We analysed 20 countries, seen here in blue, of the 58 main coffee origins. You can see the long tail stretching off to the right, which includes countries such as Ghana and Jamaica with a small number of coffee farms. And you can see we investigated most of the countries with large populations. Some of the countries here we conducted using a range of secondary research, and in most we went onto the ground to talk to farmers. So how do we estimate the farm numbers? We need to estimate the total production volume per country divided by the average production per farm. To do this, we have 3 input parameters. Firstly, total production volume, which is the easiest parameter with available data, but still needs to be triangulated between official production statistics, export volumes, and estimates from experts and institutions to account, for example, for cross-border smuggling. Then we need the yield per hectare multiplied by farm size to get to an estimate of farm production. However, many coffee farmers don't think of their farm in terms of farm size or yield per hectare. They may count their farm in terms of number of trees. In other cases, farm size is not accurate as the tree plantings are not uniform. There are coffee farms we have visited where coffee is planted around the perimeter of the farm, but no coffee is planted in the middle. So how do we derive these parameters? To get to these parameters, we need to get sample data and then follow 4 steps. Plot the histogram of sample data, decide on a population distribution curve, estimate the parameters of the distribution, the shape and scale, and then finally plot the distribution and estimate population average to get to an estimate of productivity and farm size per country. So we secured sample data sets from farm interviews or other organizations for farm size and productivity per country, and we plotted the histogram of the sample data. The histogram is a graphical representation of the numerical data and gives us a first rough sense of the data. To get a sense of distribution, do we have symmetrical data or skewed data with long tails? And this gives us an early indication of the type of distribution that we're looking at. Next, we decide on the population distribution using the Cullen and Frey graph. Plot the theoretical and empirical densities for the chosen distribution to confirm distribution choice, and then conduct hypothesis testing to see if the data follows the chosen distribution. The Cullen and Frey graph helps to recognize what is the possible distribution of population from which the sample is drawn. It plots the data against theoretical distributions. The x-axis measures skewness, that is, to what degree is the distribution normally distributed or is it skewed. Kurtosis is on the y-axis, which is a measure of distribution shape. Is it more flat or does it have a high peak? Our data set is represented by the blue dot shown in the right lower corner here in this example. Other distributions are also represented by lines, shades, or different shaped points, such as the square, triangle, and asterisk. As you can see in this example, our data was not distributed in a manner consistent with normal, uniform, or exponential distributions up in the top left corner. It had a high degree of skewness and kurtosis. Our data was closest to log normal, gamma, and beta distributions. However, beta can only be used for observations with a range between 0 and 1, which doesn't help us in this situation. So log normal and gamma were the best two distributions to choose from. The next step is to compare our data with log normal and gamma theoretical distributions. Black dots represent the Enveritas data, the empirical data, and the red and black lines represent the theoretical observations from distribution we are checking using a range of tests. We are looking to see if the empirical data plots close to the theoretical line. In our case, log normal came out better than gamma. We then conduct two additional tests to check our distribution choice of log normal. To test our data set is drawn from a given distribution, we perform the Kolmogorov-Smirnov test. This is a non-parametric test of the equality of continuous one-dimensional probability distributions that can be used to compare a sample with a reference probability distribution. The null hypothesis is that the sample is drawn from the given distribution. As a result of this analysis, we get the p-value, the upper red circle, and if the value is smaller than 0.05, we're rejecting the null hypothesis. If the value is p is greater than 0.05, then we have no evidence for rejecting the null hypothesis. We cannot say that the sample does not come from the reference distribution. If the null hypothesis is not rejected, we look at the Akaikes and Bayesian information criterion, the lower red circle, to select the better distribution. The model with the lowest BIC-AIC is preferred, and the AIC and BIC are strongly related to each other. And in our case, log normal was preferred to gamma. This is not surprising that our variables, yield and farm size, followed log normal distribution, as it is a common occurrence for many situations, especially in production or where natural processes are concerned. An example of log normal distribution would be global per capita income. If the x-axis is income, over here on the right we have a very small number of individuals with very large incomes, such as Warren Buffett, Bill Gates, Jeff Bezos, and then as we move to lower incomes, there are an increasing number of individuals until we get to the point which represents the most common income on our planet, that which occurs with the highest frequency. And then, as we continue to descend towards zero income, we still find some people with even lower incomes, but with less and less frequency as we approach zero. Once the distribution is chosen, we need to estimate the parameters of the distribution. Log normal has two parameters, mean log and standard deviation log. And once these parameters are estimated, they can be plugged into the log normal distribution equation. We have three choices in providing an average for the mean log. Mode, mean, and median are the three measures of central tendency. Mode is most often used for non-numerical variables. For numeric, mean is the most common used. But it has disadvantages with highly skewed distributions as it gets influenced by outliers. And that is what we're looking at in our case. Median divides population into two halves and is more robust for outliers and skewed distributions. So we use median in all cases as we're dealing with log normal distributions with long tails, and we didn't want our estimates to be unduly influenced by a small number of estimates with very large yields and farm sizes. Once you have the parameters, we can plot the distribution of the population and create a function, a log normal distribution of the population. This gives us a distribution of farm size distribution and yield distribution by country. And from this, we're able to generate the average farm size and average yield, which, as we've said, is the median value. In terms of the breakdown, 3 countries represent nearly half of all the world's coffee farms. Ethiopia with over 2 million farms, Uganda with 1.8 million, and Indonesia with 1.3 million farms. In total, the 20 countries we analyzed represent 10 million farms, and the 38 other countries that we did not dig into represent an additional 2.5 million farms. Once this work is completed for each country, we can produce an estimate of farms for each country and then sum them up to provide a global estimate. This generates an answer of 12.5 million coffee farms globally, which is much smaller, in fact half, the number that is commonly cited and that a casual investigation on the internet would produce. I'd like to thank once again the more than 80 institutions that gave so generously of their time and shared information and insights patiently with us to understand the nuances of the coffee landscape in their country. I'd like to thank the 20,000 coffee farmers that gave of their time so patiently. Without their consideration, none of this would have been possible. And I'd also like to thank the Enveritas team, who worked so diligently across 20 countries to complete this project and to provide a result for the public domain. We'll be sharing the country distribution functions so that other researchers that would like to use this information for their own work may do so. And finally, we'd like to thank the Benckiser Foundation, to Peter, Christoph, Stefan and the team that entrusted us with this work. Thank you.